Hi, I'm Mrs. Hannah Angelin. In this video, we are going to discuss about the analysis of three-dimensional pin-jointed structures by the method of tension coefficient. In my previous lecture, I have discussed about the analysis of two-dimensional pin-jointed structures by the method of tension coefficient. Here, in three-dimensional pin-jointed structures, we make use of equilibrium equations to analyze the structure to determine the axial forces. The available equilibrium equations are summation of all the forces along x direction is equal to 0, summation of all the y direction forces is equal to 0, summation of all the forces along z direction is equal to 0. For a space truss, for a three-dimensional pin-jointed structure, we make use of these three equilibrium equations. Next, let us consider an element, axial element of length Lij. Near end, let me take it as I, and far end, let me take it as j. This is located in x, y, z plane in three-dimensional. The tension or the force in the member is denoted as Tij. Let us assume tension. The coordinates of I are given as xi, yi, zi. Coordinates of j is given as xj, yj and zj. Length of this member can be determined by root of xij squared plus yij squared plus zij squared. So I can write xij as xj minus xi. I told you I is the near end, j is the far end. If I write xij, I write xj minus xi. That is the x coordinate of the far end minus x coordinate of the near end. Tension coefficient is denoted by Tij. It is given as force in the member to the corresponding length of the member. To determine the force, I can find out the value of length and tension coefficient and multiply to get the value of force. Let me discuss some worked out examples. So this is the plan of a tripod. It has three legs, DA, DB, DC. Based upon the lengths being given, based upon the height being mentioned in the problem and the loading, we have worked out these problems. The coordinates are determined based upon the length given in x coordinate, y coordinate and the vertical z coordinate. D being the apex, A, B and C are in a horizontal ground plane. D is located at some height. The heights are mentioned in the problem. So I have assumed x coordinate in this direction. I have assumed x axis in this direction, z axis in this direction and y is the vertical direction. So based upon those assumed directions, these coordinates are noted. With these coordinates, the length is directly calculated. Length of dA, it is nothing but root of xj minus xi the whole square plus yj minus yi the whole square plus zj minus zi the whole square. I is the near end, j is the far end. Now coming here, if the length of dA has to be determined, d is my near end and a is my far end. So I can write x coordinate of far end minus x coordinate of near end the whole square plus y coordinate of the far end minus y coordinate of the near end the whole square plus z coordinate of the far end minus z coordinate of near end the whole square. So near end is d, far end is a. So all these x coordinates are directly seen from this coordinate calculations and I have substituted. So see here, for xa, x coordinate of a is 0. I have written here 0. xd, x coordinate of d is 3. Directly I have written 3. Same way, y coordinate of a is 0. I have written here 0. Y coordinate of d is 4. I have written here 4 and so on. So we have calculated the length of each member LDA, LDB, LDC. So D is near end, B is far end. Here D is near end, C is far end. So correspondingly, length of each member is determined. Let us take it as step 1. So next, step 2, we need to determine the tension coefficient of each member. So here we make use of the three equilibrium equations, that is summation of all the x direction forces equal to 0, summation of all the y direction forces equal to 0, summation of all the z direction forces equal to 0. We have these three equations because now we are discussing three-dimensional structures. So let us consider a joint D. I have drawn a free body diagram. So there are three members coming out from joint D. Let us take the tension coefficient on each member as TDC, TDA, TDB. I have started with the notation D because I am going to consider at joint D. Here there are two loads, 120 kN and 100 kN. I should fix in what directions they belong. So this direction, this 120 kN, check in the given diagram. I have taken Z coordinate along this direction. So 120 is along positive Z direction. Check this 100 kN, it is along the positive X direction. So at D, I have two loading. One is Fx and the other one is Fz. Fx is positive, same way Fz is also positive. So we write equilibrium equations to determine the unknowns. So sigma Fx equal to 0 is my first equilibrium equation. That can be written as summation of all the x direction force is equated to 0. It is written in such a way that x coordinate into tension coefficient of each member meeting at joint D plus 100 kN, that is an x directional force going in the positive direction at D. So I write the coordinate of x dA as xa minus xd. I told you D is the near end, A is the far end. So I write xa minus xd, or in other words, x coordinate of the far end minus x coordinate of the near end. Same way for the next, for x dB, I write xb minus xd. For again dc, I write xc minus xd. All these terms start with the lettering D because I've started analyzing at joint D. I substitute the values of x coordinate. Check here, I've written my coordinates here for each node. My x coordinate for A, that is xa. X coordinate of A is 0. I substituted 0. X coordinate of D. X coordinate of D is 3. I put here 3. Next one, x coordinate of B. X coordinate of B is 0. Here 0. X coordinate of D. X coordinate of D is 3. I put here 3. And so on. So I have formed relation with my first equilibrium equation, sigma Fx equal to 0. Next equilibrium equation is sigma Fy equal to 0. Y coordinate of all members meeting at joint D into the corresponding tension coefficients plus any y directional force. All these are summed up and equated to 0. Since there was no y directional force at joint D, we did not put any force here. YdA can be written as YA minus YD. A is my far end, D is my near end. So far end minus near end. Both are y coordinates. Same way for the rest. So second equation is formed. Next equation, summation of all the forces along z axis is equal to 0. Here, z coordinate of all the members meeting at joint D into its corresponding tension coefficient plus any z directional force acting at joint D, summation is done and equated to 0. Same way for ZA, I write ZA minus ZD, far end minus near end coordinate. And I have substituted from the corresponding coordinates and equation is formed. So simultaneously solving, I get the values of the three unknowns TA, TB and TC. Only 3 legs are there in a tripod. For these three legs, we have determined what are the tension coefficient. So our next step will be the calculation of the axial forces with the help of these tension coefficients. I have written members Lij, that is the length of each member we have determined already. Tension coefficient of these three members you have determined now. Force can be calculated as the product of length and its tension coefficient. So when the answer turns out to be a negative value, it is a compressive member. If the answer turns out to be a positive value, it tells it is a tensile member, or the force in the member is compression and the force in these members are in tension. So numerically we have calculated and pictorially represented in the form of axial force diagram. I have shown the directions as well as the magnitude of the forces. So we have seen how the axial forces in the legs of the tripod can be determined by the method of tension coefficient. Let us see another problem. This is the same as that of tripod, but if the legs B, C, D are connected in the form of a triangle. The apex height from the ground level is mentioned in the problem, but x, y coordinates are not given. We have assumed one face is in line with an axis. Let us assume it is along x-axis. Point E is the midpoint of CD and point F is the midpoint of BE, that is given in the problem. That is the load 80 kN hanging vertically down from A. So we can find the value of x coordinate and y coordinate for joint C by using cosine formula. If you refer this, you can understand. I have related the cosine formula with our triangle which is given in our problem. The sides of the triangle are known, which is given. So with those sides, I have used cosine formula and determined what is the value of phi, that is the angle included at B in the base triangle. With phi, I have determined the value of x coordinate and y coordinate of C. The x coordinate of joint C is BC cos phi. The y coordinate of joint C is BC sin phi. Since B, C, D lie on the same plane, that is in the ground, C will not have any z coordinate, that is shown here. Joint B is taken as origin, so the coordinates are 0, 0, 0. And the corresponding joints coordinates are mentioned here. Since E is the midpoint of CD, this is given in the problem. So whatever coordinate we have in C, x coordinate, and whatever coordinate we have in D, that is x coordinate, the summation has to be done and divided by 2 to find the midpoint. Same way y coordinate, same way z coordinate. And one more, F is the midpoint of BE given in the problem. So B coordinate is given, E coordinate is determined, midpoint of these two has to be determined. X coordinate of B plus x coordinate of E by 2 will be x coordinate of F. Y coordinate of B plus y coordinate of E by 2 will be the y coordinate of F. Same way z coordinate. Now check, A is given as it is vertically above F. So whatever is the x coordinate and y coordinate for F, that will be the same for A except it is vertically above F. So it has some value along the z axis. So it is taken as vertical axis, z axis. The value given in the problem is 3 meter. So A is located at 3 meter above F. So the value of z coordinate at A is 3. So let us analyze each joint to determine the tension coefficients. In turn, we can find what are the axial forces in the members. So at joint A, I have drawn the free body diagram. There are 3 members coming out. So I can start from joint A. I have 3 equilibrium equations being space truss, sigma fx equal to 0, sigma fy equal to 0 and sigma fz equal to 0. Sigma fx is a summation of all the x coordinate and its corresponding tension coefficient with any x directional forces. Second equilibrium equation, with y coordinate and its corresponding tension coefficient with any y directional force. Third equilibrium equation with all z coordinates into the tension coefficient with any force along the z direction. Each term lettering starts with A, telling that the joint A is considered and it is analyzed. So while writing three equilibrium equations and simultaneously solving, we get the values of the three tension coefficient in the three members. With the help of these three equilibrium equations, we write equations to solve the unknowns, that is, the tension coefficient in the three members meeting at joint A. That is what is done here. Next, we'll go to joint B. Again, we have three members joining at joint B. One member value is already known, that is TAB is known already, and that answer I can take it for TBA. I've already told you Tij is equal to Tji. So TAB is minus 13.35. The same answer is TBA, that is minus 13.35 kilonewton per meter. The two unknowns here, TBC and TBD, has to be determined. I make use of any two equilibrium equations. So let me start with sigma x and then go to sigma y. Here x coordinate into tension coefficient of each member and any x directional force, summation is done and equated to 0, equation is formed. Here all lettering is starting from B, telling the joint B is considered for analysis. Next, sigma Fy, second equilibrium equation, all y coordinate and its corresponding tension coefficient. Since there is no external load or reaction, I just put equal to 0. So simultaneously solving, I get the two unknowns TBC and TBD. Again, three members join at joint C, out of which two member values are already known, that is TCA and TCB. Only one unknown, that is TCD, has to be determined. So I can make use of any one equilibrium equation to determine the one unknown. So I have taken sigma fx equal to 0 and a relation is written, and finally known values are substituted and unknown is determined. So after determining the tension coefficient in all the members, I can write in this tabulation to find the axial forces. All the members of the truss are mentioned here. Length of each member can be determined directly with the relation. If it is LAB, it is root of XB minus XA the whole square plus YB minus YA the whole square plus ZB minus ZA the whole square. So I can directly find the value of length. Like this, I can find for BD and so on. So I can find out and write it directly Lij. Tij is the tension coefficient we have determined in the previous step. Next, force can be determined as the product of length and tension coefficient. If the answer is a negative value, then it is a compressive force. If the value is positive, then it is a tensile force. So numerical calculations are represented in the form of a pictorial representation called as axial force diagram. Let us see another problem. It is a space truss. The dimensions are given in the problem. Based on it, the coordinates are fixed. Let us take A as origin. There is a force acting along ED, that is 100 kilonewton acting along ED. It is neither along x-axis, neither along y-axis, nor along z-axis. So we need to determine the components of force 100 kilonewton along the three axes separately. So here the load is given as 100 kilonewton. P vector is magnitude of P into unit vector along the load. What is the vector along the load? It is ED. 100 is the magnitude. Unit vector along ED can be determined as OD minus OE by the magnitude of ED. So 100 into OD can be written as with the coordinates 0i, 0j minus 3k, that is written here, minus OE. With the E coordinate, I write 2i plus 3j plus 0k. That is what is written here. Divided by root of I squared plus j squared plus k squared. Finally, the force along I, j, k directions are determined. The coefficient of I vector is the magnitude of force along x direction. Coefficient of j vector is the magnitude of force along y direction. Coefficient of k vector is the magnitude of force along z direction. That is given here. Px, Py, Pz. So we have determined the magnitude of force 100 kN which is in space, which is neither parallel to x, y or z direction. Okay, we have resolved and we have determined what is the force along each direction separately. So we are going to make use of these forces when we consider joint E for our resolving. Let me start from joint E. There are three members unknown. So I have made a note about 100 kN. This has three components. When I take sigma fx equal to 0, I should consider px. When I take sigma fy equal to 0, I should consider py. And when I take sigma fz is equal to 0, I should consider pz. X coordinate of all the members meeting at the joint is considered with their tension coefficient. And I have a force px. The value of px is minus 42.64. That is taken. And equation is formed. Sigma fy is equal to 0 is my second equation. Y coordinate of all the members meeting at joint E with the y directional force. Equation is formed here. Third equation, sigma fz equal to 0. Z coordinate of all the members into tension coefficient plus pz. Simultaneously solving, we get the tension coefficient of the three members meeting at joint E. At joint F, we have four members, out of which EF, that is FE was determined already. So tension coefficient of FE is same as tension coefficient of EF. That is shown here. Same way we have written three equations, sigma fx equal to 0, sigma fy equal to 0 and sigma fz equal to 0. I can determine the three unknowns, that is the tension coefficient of these three members, FB, FA and FD. That is what is shown here. After finding the values of tension coefficient of all members, I have substituted here length I can determine based upon the relation already discussed for each member. So length is shown here. Tension coefficient we have determined. Product of these two will be the forces and finally the nature of force. Member BE, members CD and DF were zero force members. So numerical value of axial force is represented as an axial force diagram showing the magnitude and direction of forces. Two diagrams are shown. One is plan and the other one is elevation. In plan, x direction and z direction is assumed. In elevation, y direction and z directions are assumed. The distances along x direction, along y direction and along z direction can be taken from these two plan and elevation diagrams taken together. So length of each member can be determined after fixing the coordinates based upon the length given in the problem. We have considered the origin as O 0, 0, 0 which is away from the structure. Origin can be taken as any node in the structure or it can be taken away from the structure, but the distances has to be considered carefully while fixing the coordinates for each node. Distances along x, y and z directions are mentioned in plan and elevation. You should check before fixing the coordinates. So first step, we have calculated the length of each member by root of xj minus xi whole squared plus yj minus yi whole squared plus zj minus zi the whole squared and taking the root. So let us begin analysis from a joint where we have three member forces as unknown. Hope you can see the given diagram. We are going to begin with a joint where we have three member forces as unknown. Let me start from joint E. So at joint E, we have EB, EA and EF. That is what is mentioned here. Apart from these members, there is a load 80 kN acting in plan. At the same joint, in elevation, there are two loads being shown, one 100 kN loading and the other is 80 kN loading. So in plan and in elevation, Z axis is shown. Both 80 kN is a single load acting along Z direction. It is seen in plan as well as in elevation. So these are not a pair of loads, it is just one load acting along Z direction. That is what is mentioned here. Fz is 80 kN at E. Next, 100 kN is acting vertically down. I have taken y axis in this direction, so it is opposite in nature. So Fy is minus 100. So to resolve the tension coefficient in the three members at E, that is to find TEA, TEB, TEF, I write three equilibrium equations and simultaneously solve to get the unknowns at joint E. At joint F, there are four members coming out from joint F. There are a set of loads 120 kN seen in plan and in elevation. Now check the direction. 120 kN in plan is in the opposite direction of positive x direction. So Fx is minus 120. In elevation also I have the 120 kN loading, but that load is along y direction but in the opposite direction. So I write Fy as minus 120 and along z direction no loading. So considering the equilibrium equations along x, y and z directions, we have solved to determine the unknowns along the three members, that is Fb, Fc and Fd. Ef was already known, so we take the answer for Fe and substitute to get the values of the other unknowns. So simultaneously solving, we get the values of the unknown tension coefficients. So after determining the tension coefficient, we write the members, length of each member, tension coefficient of each member and the corresponding force by finding the product of length and tension coefficient. I have written C telling these forces are compressive in nature and T denotes tensile in nature. These numerical values are represented as an axial force diagram pictorially, showing the magnitude and direction of force in each member. Hope you have understood the analysis of three-dimensional pin-jointed structure by the method of tension coefficient. If any doubts, you can just post in the comment box. Thank you.